So last lecture was cosmology, right? I'm going to start out with some current events. Just today, like, I became aware of this paper like 1 hour ago. Like, obviously I'm going to react to this skeptically because I haven't read the paper fully, but it seems to be proposing something very interesting. They took data from a space telescope called Planck that's observing the cosmic microwave background, which we talked about in the cosmology lecture. And what they claim is that one like pretty good way of explaining the data from this spacecraft is if you have a closed universe. And we talked about curvature in the last lecture, right? So what they're saying is the curvature of the universe is positive with pretty high confidence. And so that would imply pretty interestingly that the universe is finite, which is not a given and very, very unusual. It also implies if I take two lasers and they're perfectly parallel to each other and I shine them out like arbitrarily far, over really long scales, those parallel lasers will actually intersect, right? And so this is like, and they're claiming at more than the 99% confidence interval. So if you know like statistics, they're claiming I think 3.2 sigma, 3.4 sigma, something like that. Yeah. So this is like a pretty groundbreaking paper that was released today, and I'm very skeptical.
Questionably groundbreaking.
What?
Questionably groundbreaking.
Yeah, questionably groundbreaking. Yeah, for sure. But I mean, it's pretty interesting. Things like this get disproven. There was a result a while back claiming that they found like superluminal or like neutrinos that travel faster than the speed of light, and then they had to retract the paper because they realized there was some error in their measurement or something.
Because of one wire was unplugged somewhere in CERN, the particle collider, something like that. And then that was the reason they found faster than light.
So sometimes things like this get disproven. But if this is real, it would be obviously very, very groundbreaking and very mind-blowing. Because partly because it implies a finite universe. Okay, so don't go directly to that. So last week we sort of discussed cosmology, which is like on the largest scale of things, right? As large as you can get. This week, can you raise the projector actually?
I'm sure.
Yeah, we're going to discuss quantum mechanics, which is on the smallest scales, and I hope to make it evident why this branch of physics applies to the small scales in due time. I'm going to start with a question. So it's a sort of arbitrary question, but you'll see why it's important in a second. So if I have a setup where I have like an object with two slits in it, right? And I have like something shooting out particles here, like a gun or something. It's shooting out particles, right? And I have a screen at the back. These slits are supposed to like isolate the particles in one particular stream, right? How would you guys expect the pattern would look like on this back screen? Like the bullet holes or whatever. So like discuss that with your partner. How to figure out. So some of you have clearly heard of this example already. That's okay. Has anyone not heard of this like example before? The idea of the double-slit experiment. Has anyone not heard of this? Okay, well, that's okay. So does anyone have any idea what you'd expect to see on the? Yeah.
Intuitively, there should only be 2 points where the particles hit, or two areas of concentration.
Yeah, so like particles can go through this slit and end up here, right? Particles can go through this slit and end up here. You wouldn't expect particles like here or here or here, right? There's no way a particle can get there, right? So in the, I'm going to say like early 20th century, because I don't know the exact time, people did this. I think there was someone named Young who did this. except with light, right? And at the time there was this confusion: is light a particle or is it a wave, right? He did this with light. He took a laser beam, shown it at, I don't think he had lasers back then, but he took like a source of light, right? Shown it at a slit, right? And recorded the pattern that it made on a projector screen, right? You just take a slit. This is fairly easy to do. In fact, I will try to actually show you at some point. It's something that you can do sort of with a laser and a slit and like a projector. It's pretty easy to do. And he got like a really weird pattern. He got a pattern like basically it looked something like you have like something like this, right? And on the side of this is exceptionally weird. How would you expect the pattern to look like this when, and like to be clear, like if you did this with like slits, you'd end up with like fringes basically across your projector screen. And so this seems really weird until you realize that there's a macroscopic situation that looks exactly like this. And that is, if you treat what's coming out of this as a wave, the wave would hit the slit, right? And it would interfere with itself so that you'd end up with a pattern like this. So I'm going to show you like a diagram of this real quick. This is just a GIF. The color's kind of off, but this person is on a lake basically, and he's just like hitting the lake with two small objects, right? Each object is creating ripples, and as the ripples, each ripple can sort of like, ripples can add together, right? If you have a peak of a ripple and you have a peak of another ripple, you end up with a really high peak. And if you have like a trough, the bottom of a ripple and the top of a ripple, and they move over each other, they sort of cancel each other out, and you end up with so over here, you see when it flips, you see those lines where you end up with basically no wave, right? And that's where the waves are interfering with each other. And so if you were to put a projector screen here, on the back, you'd end up with exactly this kind of pattern, right? You'd end up with a pattern of fringes on your screen. And so this would model the situation perfectly. Simultaneously though, there was an observation of a phenomenon that seemed to contradict this. And that is the photoelectric effect. So if you take light and shine it on a metal, as it turns out, the light can dislodge some of the electrons in the metal, and you end up with a current. So that's like the principle of the photoelectric effect. Now, people found out that if you turn down the amount of light, you'd expect, if you're treating light as a wave, right? You're just reducing the amplitude of the wave. You'd expect that you just get less electrons dislodged, right? But this isn't the case. In fact, if you try this, at some point there's just a cutoff, right? And below that, you can't get any electrons dislodged. And so this seems to contradict itself. Like in one case, light is behaving like a particle. In one case, light is behaving as a wave. And this is like very strange. So now we go like we can sort of ask the next question: what if you do this experiment, except you turn down the light to the point where like there are like your phone, for example, has something like a CCD sensor that records light, and that's how you take pictures, right? That's how your camera works. You can have a CCD sensor as your projector here that counts every photon as it comes in, and you turn this light way down so that you can actually have like countable number of particles coming out of this source, right? And you see a particle go through, right? So now, any ideas what would happen here if you turn the light down and you actually have like individual particles coming out of this, and going and hitting the projector screen. What pattern would you expect on this back? So discuss that with your neighbor.
Off each other as much,
I want you to think specifically, like, now you can almost view this as like individual light particles. We're counting light particles here, right? So you can almost think of it as like individual particles coming out of this and like ending up on the screen, right? We've turned the light down to that extent. Does anyone have a guess? What would happen? Any guesses? Any guesses? Anyone have an idea? Do you guys need more time to discuss? Go ahead. Yeah.
Well, I was thinking if you only shoot a couple particles,
Mhm.
it's less likely that they're going to interfere with each other.
Mhm.
And so maybe because of that, they're only going to appear in 2 spots.
Okay, so you think they're, who agrees with him? They're only going to appear in 2 spots. Or mostly only 2 spots. Who thinks that it's going to be the same as before? All right, looks like none of you think it's going to be the same as before. Well, actually, it's the same as before. Sorry. This is like, and I agree with you, this is really, really strange, right? On the face of it, we're putting out like a countably finite number of particles, right? And like a specific particle, if imagine tracking it as it moves, right? How does it end up here? How do you count a particle, a single particle ending up here, right? We're not viewing them as waves, right? If we're viewing them as particles, how does a particle end up here? This seems really, really counterintuitive. And as it turns out, this is reality, right? If a particle comes out of here, it actually can still interfere with other particles. During the interference pattern, it can end up somewhere here. And so this is like one of the key points of quantum mechanics. And this is the idea of wave-particle duality. So I want to clear up some misconceptions about wave-particle duality. It isn't that first of all, that I've heard, we don't know whether it's a wave or particle. We know exactly whether it's a wave or a particle. It's also not that it's neither a wave or a particle. And it also doesn't say that in some situations we have to treat it like a wave, and in some situations we have to treat it like a particle, and the physics just doesn't know which one to actually do. That's not how it works. It's that particles like this have properties of waves and they have properties of particles. The property of the particle is that they're countable, right? You can ask, it's a valid question to ask where exactly a particle is. And like, you can, like, as with the CCD example, you can actually count particles, like off, one by one. And the property that they have that's like a wave is that they interfere with each other. And so, like, the real answer, how physics actually works, is that there are properties of both, specific properties of both that we observe when we're looking at particles like this. Now here's another question. What if I tried to actually track the path of a single photon? A photon is a particle of light, right? What if I tried to actually track the particle of a photon as it passed through the slit? What would I see? So, discuss with your partner again, or your neighbor. What would you see if you actually tried to track the path of a photon? We saw in the last example, the photon ended up here. What would happen if we tracked it? I'm not saying we're shooting out a single particle. We're shooting out like a very low number of particles such that it forms I'll actually answer this question in a little bit, but I get what you're asking. We're shooting at enough particles, there's a between one versus a single particle. I'm not sure. Yeah. So if I shoot up to a single particle, well, in the case of a single particle, the particle can't actually interfere with itself, because it still has a wavelength, right? And so in that case, it would just be uncertain where it would land. It could land in one of it could land on any of the physics. Yeah. So this is basically like if I shoot out more and more and more particles, or if I take a situation where I have a single photon, I shoot it, figure out where it goes, right? And I do this experiment again, and I keep doing it over and over and over again. Then you'd end up with a pattern. So one particle can actually interfere with itself, and that's perfectly valid. Yeah, exactly. Yeah, so that's a good question. I'm not saying that the particles have to interfere with other particles. An equivalent example here is, let's say I just shoot out one photon, right, from this, and I record where it goes, right? Then I repeat the experiment again. I shoot out another photon, and I record where it goes. And I do it again, and again, and again. And like, do it like an arbitrarily large number of times. What would the pattern of all of the particles landing, what would it look like on this screen? So this situation is different from the last one, that I'm not shooting out particles at the same time. So one particle can't interact with another particle. It can't interfere with another particle, right? Turns out you get the same answer, right? This implies that particles can interfere with their own waves, right? So if I shoot out a single particle, it has a wave, and that wave interacts with its, it interacts with its own wave and interferes with its own wave and can end up like anywhere on this screen, right? So that's an important distinction. So does anyone have an answer to the question of what I would see if I tracked the particle? Anyone have any guesses? Anyone? All right, so we had a situation where we shoot out a particle, right? And it ends up on this screen. And like the particle weirdly ends up like in a place that it doesn't seem to be able to go to, right? If we were to actually like record and measure where the particle is moving, this pattern on the screen would change to just two lines over here. So in other words, the act of measuring actually makes the system collapse into this configuration, into the configuration that we expect if we're just shooting out particles. And I want to emphasize that this isn't some weird like spooky magic. It's in some sense it's strange and it's unexpected, but it's not like completely magical. This is something that happens, and it's in a way it's because the act of measuring changes the system, and it's not like this isn't like pure magic, because like if you measure anything, you can sort of change the system if you're not careful. Quantum mechanics just says that there is no way to measure without changing the system. Right?
So how do you actually measure something? Like, how would you actually know which slit the particle went through? Maybe discuss that? Like, what are ways you could figure that out?
This is for like a subatomic particle, right?
Yeah.
Anyone have any ideas? Maybe.
Like, I've sort of seen some explanations where they like put a little camera in front of the slit, and this is really misleading because it makes you think that like you're just passively observing or somehow getting information about which slit the particle is going through. But it's worth thinking about what measurement actually means in this context.
So the answer to that is basically there's no way to measure it. You can't just like put a camera here and track where the particle is going, because you can't measure it that way. The only way to measure it is by actually like shooting something at it, trying to record where it goes. Like, the only way to measure it is by doing things that would disturb the system. So, in effect, like the act of measurement changes the system. This is one other important, yeah?
How does it actually disturb the system?
What do you mean how? Like
why, I don't understand why measuring it would affect the system at all.
I'm saying that there's,
it does, but
yeah. I'm saying that there is no way to measure where a particle is going without somehow interacting with the system, right? Like, how do you make any measurement? You have to like, I don't know, like compare it to something, or like, if you want to know where something is going, like you're sort of, if I'm like watching an object, I'm sort of receiving the light coming out of that object, and using that I can figure out where it is, right? But for systems like this, there's no way to measure it without actually interacting with the system, without like bouncing a particle off of it or something like that. And there's no way to make the measurement. This is like a fundamental thing. This isn't just like an experimental like problem that we have. Fundamentally, there's no way to measure the system without disturbing it. And as a result, if you try to measure the system, it'll collapse into this state. It'll collapse into one of, so there's, and I'm not going to go into it in this lecture, but there's a popular paradox called Schrodinger's cat, and this sort of like encapsulates this problem in a sort of like macroscopic example. But so okay, this is fine. Yeah.
I sort of have the same question as him. So like, say if you point like a really high frame rate camera at it, like how is that affecting the system?
Okay, so I think the way of thinking, how is it that you see light?
How does a camera work? Think about this camera. Like, is this camera just like observing? It's not really. Like, what's happening is particles of light are bouncing off things in this room and entering this camera, right? And that's how the camera actually works.
Right.
So now if you think about a camera in the slit sense,
Right.
like you have to bounce something off of a particle in order for your camera to detect it.
Right.
And so bouncing that particle off in a loose sense, that's affecting the system.
It's disturbing the measurement, right? Okay, so okay, so I want to quickly like extend this example. So we talked about light, right? Light is a particle in a wave. Okay, so that's interesting. You sort of understand what light is slightly better, or maybe you don't understand it less. Either way, what if we do this for something that's slightly more familiar, or maybe or slightly different? Let's try it for an electron, right? Electrons are around atoms, and we're sort of familiar with regular matter. Light is sort of abstract. So what if we tried the same experiment with an electron? Can anyone guess what the pattern you'd observe are? So we think of electrons very much as particles, right? Like electron orbiting around the nucleus of an atom. So what happens if I take an electron and I try the same experiment? Raise your hands if you think you'll end up with two spikes on two like lines on your projection screen. All right, raise your hands if you think you'll end up with interference fringes. All right. So you're correct, of course. If you take a source of electrons and you put them through a slit, you end up with the same interference fringes. And this is really cool because it implies that electrons, which we view as particles, have the same sort of behavior. Now, what if we take like something even larger than electrons? What if we take like atoms, full atoms? Raise your hands if you think that these will display two lines like this. Raise your hands if you think it'll be an interference pattern. All right. Okay, your guess is still correct, right? We have two interference patterns. So now let's take an even larger example. Let's say we're dealing with bullets. Now, raise your hands. Bullets are just like collections of atoms, right? Raise your hands if you think that this will form like two fringes like this. All right, raise your hands if you think it'll form an interference pattern. not very many of you think that this will form an interference pattern. So what gives? So as it turns out, as you get larger and larger, or as the particle gets larger and larger, you sort of intuitively have this understanding, right? As the particle gets larger and larger, somehow the waviness of this particle goes away, right? Because you don't see like bullets diffracting with themselves, like interfering with themselves, and displaying this kind of behavior. You don't see cars like diffracting off the highway or whatever. Like it seems very much like macroscopic objects don't display this behavior. But if you take like microscopic objects, people have even done this with, I don't know if you probably haven't heard of like buckyballs, or like if you look at, imagine like a soccer ball, right? And like a soccer ball shape, and you replace all of the corners of the soccer ball with like carbon atoms. That's like how a buckyball looks. These are like really, really big molecules, right? And they've done this experiment where they shoot buckyballs at a double slit and then actually record an interference pattern as they fall in the slit, right? These are huge molecules. Then you can think about doing this with like proteins or like even bigger molecules, scaling up all the way to a bullet, right? And as it turns out, the waviness, or you can sort of imagine as the wavelength, is proportional to some number, this constant, or h, right, over p. So, and p here is the momentum. We use the letter p to represent momentum. This is a constant, and this is the momentum. So as you, like, if you try this with larger and larger particles, you might remember from classical dynamics that the momentum is related to the mass of an object and its velocity, right? So if you try this with larger and larger particles, you're trying it with more massive and more massive particles, and you end up with particles that are so massive that this wavelength is so small that effectively you're dealing with a particle, right? But for objects with really low masses or really low momenta, like light, right? This effect is very real and very observable, right? So this is why quantum mechanics applies more to small objects than it does to large objects. It isn't because there's some fundamental gap between quantum mechanics and like other branches of physics. There are some gaps there, but it isn't related to this. It's because this is called this wavelength is called the de Broglie wavelength, and it's very important. This sort of it tells you how quantum an object is behaving, and this number will tell you whether like the wave nature of this object is appreciable or not. So we've gotten a glimpse of how things behave in quantum mechanics. I want to try and show you some. So a lot of you might have heard about things from quantum mechanics, first of all, the word quantum, right? Quantum implies that like if you say something is quantized or you say something is quantum, you're saying that it's discrete, right? You're saying that it can be like there's something that's like there's like a step function relating to it. Does that sort of make sense? And so in that sense, where does this come from, right? Where does the quantum nature of things come from? And so I'll show you how a lot of this stuff coming out of quantum mechanics is like a natural consequence of treating things like waves at really small scales. And so the first example I'm going to give of that is called a standing wave. And so in this example, I'm going to take waves that a lot of you are familiar with, like a guitar string. Guitar strings make waves, and those waves basically turn into pressure waves. Those pressure waves are sound, is what you hear. Right? And so some of you might have heard that music, like all sound is like are waves, right? When you're dealing with like when you strum a guitar string, what's coming out of that is like a pressure wave that you can hear, right? And so if I have a guitar string and I hold it down on two ends and I strum it, what happens to the guitar string? Right? So when I try this, I'll get a wave, right, on this guitar string. And so if you actually slow that wave down, what it will look like might look like this, right? Or it might look like this. Or it might look like. The important thing about this is that on the ends, the wave can't move, right? So it's constrained by the fact that the ends cannot move. So you can't have a wave that looks like this because you're holding the ends down, right? So because of this, you sort of have a quantized wave that you can expect from a string like this. So you can only have configurations like this, or any like half of this, or half of that, and so on and so forth, right? And so, as it turns out, the same behavior applies to really small systems in quantum mechanics. If I have a particle, let's say I put a particle in a really, really like steep box, right? And as we've seen, particles like this have wavelengths, right? So I can have a wave like this, right? Importantly, like the particle can't at the edge of this box, you know that like the particle can't be over here, right? So at the edge of this box, we know that the particle can't exist, right? It can't go into the wall of this box. So we know that it must be 0 on these ends, and so the particle can have a wave that looks like this, or it can have a wave that looks like half of this, or it can have a wave that looks like a quarter of this, and so on. Right? So, and this is important because the wavelength of this particle is related to the energy of the particle. So if you've ever wondered why, like in atoms, right, you have like energy levels. They talk about like energy levels in atoms. This is the reason for that, essentially. You have like distinct energy levels because there are only a certain number of allowable waves that exist, and waves in between those are not allowed. So this example is called a standing wave, and there are animations that I can show you later that that'll show you how standing waves look for like guitar strings or situations that are like on a lake or things like that. Standing waves are a direct consequence of the fact that you're basically dealing with waves. They aren't anything particularly special. But in quantum mechanics, those standing waves translate to the fact that energy is quantized. And this is really important. But energy isn't quantized everywhere. If I have a particle that's not in a box, that's just in free space, right? Let's say I take an electron and I have it in free space. This particle does not have anything holding it down on the ends, and as a result, the energy is not quantized. I can have any energy. This electron can have any energy, and it's allowed, right? But if I have the particle in a really steep box, this is called a potential well. Atoms happen to be like this. Then I have only a certain number of allowable energies. I have energy becomes quantized. And as it turns out, there are other things that are quantized that are even more mind-blowing that come out of this, like the spin of an electron. And we'll talk about this more on Wednesday. But the spin of an electron, like you think of spin as like a very like continuous quantity in our world, right? Something can be spinning in any direction, and it can be spinning in any way, right? But this same thing results in things like spin being very, very quantized. And so, for example, electrons have only 2 allowable spins. So this is pretty cool. And then, so the next topic I want to cover is another consequence of the wave nature of particles. So some of you might have heard of the uncertainty principle. Like there's a famous adage that Heisenberg is like on the Autobahn and speeding, and he gets pulled over, and the cop asks him, "Do you know how fast you were going?" And he says, "No, but I know where I am." So like this is a joke, and it's supposed to. It talks about how. So Heisenberg created a principle called the uncertainty principle. And he said that if you know where a particle is with exact precision, you don't know what its momentum is. And if you know exactly what the momentum of a particle is, you don't know exactly where it is. So I can show this in equation form with delta x, delta p is, let's see, less than. So x stands for position here, and p stands for momentum. So if I have, and this is a constant again. So if I have like a perfect knowledge of x, that means this is very close to 0. That would mean that this is greater than. That would mean I cannot have a perfect knowledge of a momentum. And if I have a perfect knowledge of momentum, I can't know the position perfectly of a particle. And on the surface, this seems sort of like, why does this matter? Why is this important? But it can yield some pretty strange looking results. Like for example, if I'm in a car and I'm like speeding down, right? How does it make sense that I know my position and I don't know, like I know exactly where I am, but I don't know what momentum is? And as it turns out, this can be seen pretty easily if you treat things as waves. So let's say I have like a rope. And I told you earlier that in quantum mechanics, our wavelength is related to the momentum of an object, right? So I have a rope, and this is attached to a wall over here, right? And like, and I give the rope a little pulse, right? So this is my hand. It doesn't make sense for me to ask where exactly is this pulse. Raise your hands if you think it makes sense for me to ask where this pulse is. Raise your hand if you don't think it makes sense to ask where this pulse is. All right, so I'm going to argue that you can tell where this pulse is. It's basically right here. But let's make this example slightly more exaggerated. I'll give it like a really extreme pulse, right? Like that, right? Now it sort of makes sense that I can say very clearly that this pulse is right over there, right? I know the position pretty clearly. It's pretty clear to me that I know the position of this. Now, does it make sense for me to ask what the wavelength of this pulse is? What is the wavelength of that pulse? Why do you think it does make sense?
Oh, wait, no. Maybe it doesn't because, well, maybe it does. Wait, does there have to be multiple waves in order for you to know the wavelength?
Yeah, like sort of like you can think about this like there has to be multiple ways for you to know the wavelength exactly. Another way you can think about this is if you've done, even if you haven't done like Fourier analysis, you might know that like you have sine waves, right? If I have sine waves of different frequencies, I can sort of add these together. I can add sine waves, right? If I have a sine wave like this, and I have a sine wave like this, they have the same frequency. If I add them together, right, I get a flat line, right? Now let's say I have sine waves of different frequencies, and I add them together, right? What would I get? It turns out in order to construct something like this, I have to add sine waves of like a lot of different frequencies, right? A lot of different wavelengths. And this means that if I'm adding sine waves of like every single wavelength, the specific wavelength of this is sort of fundamentally uncertain. Like you have no idea what wavelength, because there are many wavelengths you were talking about here. And conversely, if I have like if I do this example again, except this time I pulse the wave like repeatedly, right? Or I pulse the rope repeatedly, right? Now does it make sense to ask what the wavelength of this is? Raise your hands if you think it makes sense. Raise your hands if you think it doesn't make sense. Okay, so you can sort of see in this example, it clearly makes sense to ask what the wavelength is, but you can also sort of see that it doesn't make sense to say exactly where this wave is. This wave can be anywhere here. It's like it's in many places, it seems, right? So these are the two like examples. This is knowing the position with complete certainty, and this is knowing the wavelength with certainty. And of course, there are intermediate examples as well. Like I can pulse the rope like. Right? If I pulse the rope like this, I sort of have an idea of where it is. It's like somewhere here, right? And I sort of have an idea of what the wavelength is. It looks sort of wavy, and I can say somewhat what the wavelength is. But I don't know both very well. So this is sort of an intermediate between these two extremes, right? So how do I connect this to quantum mechanics? I'm actually going to argue here that this is a direct result of this is just the double-slit experiment. So when I have a particle passing through these slits, when it is passing through the slit, do I know where it is? Anyone have any idea? Do I know where it is when it's passing through the slit? Yeah, so I'm seeing some nods. Yeah, like you know where it is because you're sort of constraining its position. You know, when it's passing through this slit, it has to be somewhere here. So I have a pretty good idea of where it is, right? So all of a sudden, when I know where it is, so here I was talking about wavelength, right? But we know in quantum mechanics the wavelength is related to the momentum of the particle, right? And so this uncertainty principle says that if I know the position of something, I don't know its wavelength, and if I know I don't know its momentum, and if I know its momentum, I don't know its position. And so the same thing applies here. If I know this particle's position when it's passing through the slit, which I do, suddenly I lose an idea of its momentum. And if you, like, even in classical mechanics, momentum is equal to its mass times the velocity, right? So you can sort of see this as I don't know where it's going. It can be going in any one of these directions. And so suddenly I lose an idea of where it's going. It can end up here, it can end up here, it can end up anywhere along this projector screen. And so this is sort of an example of like the uncertainty principle in action. As soon as I constrain the position of the particle, I suddenly lose an idea of where it's going. I'm going to talk about one more thing I think I have planned, which is, so in last discussion section, Nicholas talked about complex exponentials, and I'm going to give you an idea, an understanding of like one more interesting behavior in quantum mechanics that is sort of that seems sort of very, very strange at first, but can be explained through the last discussion and an understanding of how quantum mechanics works. And again, it's just a natural, it's sort of a natural result of treating things as waves. So let's say I have a particle here, and I'm passing it through some sort of wall, which looks something like this, right? It turns out in quantum mechanics, it can just go straight through the wall and end up on the other side. I can end up measuring this particle on the other side. And this seems completely strange, it doesn't seem like this is possible at all in classical mechanics, right? So how does this apply to waves? As it turns out, there's a fairly good way of describing this with waves, right? So Nicholas talked in the earlier lecture about how you can sort of look at waves. E to the I theta is equal to cosine theta minus plus I sine theta, correct? Right? So you can look at complex exponentials. If I have exponentials like this, you can look at these as like combinations of cosines and sines. And we know cosines and sines look like waves, right? So if I have a wave here, right? The way to visualize how this happens, this in quantum mechanics, this is called tunneling. Is that with 2 L's or 1 L? Tunneling? Alright, I'll do it with 1 L.
One.
Oh yeah, okay. So what happens inside this wall is that this exponent becomes imaginary. And so what I end up having is I have something like, this is sort of hand wavy, but you'll see what I mean. I times, or I squared, right? This exponent becomes imaginary because I end up with one more I here times, theta is imaginary, so I end up with something like I squared. And we know I squared is negative, so you end up with e to the negative something, right? E to the negative something is an exponential decay function, which looks like this. And so this means that you can sort of see this as like the probability of the particle is sort of exponentially decaying the wider this wall is, right? But that means right over here, at the other end of this wall, there's some finite probability that this particle is still here, right? And this means that this particle can basically go straight through the wall and then end up on the other side. There is some probability of that happening. Now, not every particle you won't see this for every particle, but as it turns out, if you have enough particles here, some of them will just end up on the other side. And this is a pretty this is something we actually observe. For example, in the sun, it turns out there was a problem for a while where they couldn't get like atoms to fuse together. They couldn't get atoms to actually fuse together, hydrogen to fuse together to form helium in the core of the sun when they ran models using basic physics. And the way to resolve this is particles can actually tunnel. Electrons can actually tunnel between barriers. They can literally tunnel into each other and end up fusing. Particles can tunnel together and end up fusing, and that's what resolves this crisis in astronomy. When quantum mechanics came along, finally, this behavior could be explained. Are you trying to show that?
Good. Well, yeah. Do you want to show the animations or anything? How do you want to do it?
No, I think I'm good. I think the last thing I'm going to talk about on a sort of wait, Nicholas, are you talking about entanglement?
Yeah, next time.
Okay. So I'll let Nicholas talk about entanglement. For now, are there any questions from quantum mechanics? I'm actually going to have if you can discuss about something that confused you for quantum mechanics with your partner, and then sort of ask that question. Yeah, then I can sort of answer any questions from. I think quantum mechanics is usually taught as in order to try and mystify it, to make it sound more mysterious. But I think the actual way you should approach quantum mechanics is to go the other way around. Quantum mechanics isn't particularly weird. It rises out of fairly simple things, and the correct approach should be to try and demystify it and not to try and mystify it. So, so can you discuss with your partner and talk about something that confused you, and let's see if we can come up with an explanation for it.
Yeah, I did it. Sounded it. Weird. So like the first question Wait.
Yeah.
But why?
Meanwhile, here's an animation of the double slit in actual water. I did those. So yeah, so like, yeah, so the homework's due next which homework? Oh yeah. Oh okay. Yeah.
Yeah, to clarify, so next week, prompts at 8 is due on Monday, I guess not Monday, so Wednesday.
Yeah, Wednesday, yeah.
Yeah, and then, so the dates are wrong on the document, but on Wednesday we'll post the next concept, on this Wednesday we'll post the next concept that won't be due until the following Monday. Okay. So, sorry. It's a bit
So
confusing because of the
you would sort of
acronyms.
go around and like, do you have a question you wanted, or something you wanted to clarify?
That's maybe we want. Yeah, we want to say.
I'll go first.
Yeah.
So I was confused on, I think I want a refresher on exactly what theta means in this context to
okay.
see why it would be negative when you're going through the wall.
It wouldn't be negative when you're going
Or
through
sorry,
the wall.
why is it imaginary?
Yeah.
Can I try this one?
Yeah. Theta is supposed to be like. Let's see. It's h bar. What is it again? H bar E over. It's related to the energy in some way, right?
Yeah, so it's going to be like E over H bar,
E over H bar. Okay.
which
so,
is the frequency.
okay. So you can sort of see the energy inside this and the energy is like so in quantum mechanics this is like this wall can be defined more rigorously as a potential barrier, right? And so you can we've talked about like hills and stuff to explain potential so far. Like this is sort of like a potential barrier. So this is like a hill like this, and you can sort of imagine that the energy in this would inside this you end up with an imaginary energy, and as a result you end up with, so if this is something with an I in it, you then end up with like I squared here, and then you'd end up with a decaying exponential. Is that satisfactory? Like,
Yeah,
do you want
I think so. Let me write something.
Also, maybe it'll help to remember that like a wall. Remember what we discussed in earlier lectures, where like if you touch a table or something, or try to put your hand through a table, that the reason why you can't do that is literally due to electromagnetic repulsion. So, in that sense, like trying to tunnel through a wall, you're going against the potential barrier due to the electromagnetic repulsion.
So recall in classical mechanics you have some hills like this. This is from the very first lecture. You have some particle and sort of just like sort of going on its merry way, right? And you remember that from the conservation of energy, it has some amount of energy. And then so like it might go over some, potential. And then like for example, if your particle's over here, then because of conservation of energy, you must have this much kinetic energy. Do you remember that? And so if your potential is like here, you can't like be inside, right? The way it works in quantum mechanics is a bit different because your particles sort of like described by like this exponential, right? Which is sort of like a wave, like this, kind of, right? And the thing is, in quantum mechanics, what happens is you sort of have this wave, and the wavelength will sort of depend on like how much like energy you have, kinetic energy you have. So this omega is like the energy, like within a constant, it's the energy basically. But if you're here, right? You're here. Well, the thing is like you would think you need a negative kinetic energy, right? Does that make sense? It turns out that what that actually means is that this number becomes like imaginary. It's actually like square root. This becomes like imaginary. Is that true? Yeah, I have to think about this.
This is like E minus V, right? Or sorry, E minus.
Sorry,
P.
I should say not T. I should say KX. That's better.
Yeah, and then this is something like this is potential energy minus K, right?
Other way around.
Wait. Oh yeah, other way around. Yeah.
KE minus P.
Yeah.
Right? And so when you're in here, then your potential, this number becomes imaginary, right? And
So you can basically
becomes
say like the
I
potential
something.
energy is greater than the kinetic energy over here.
And so you'll get e to the like minus something. And so actually instead of being a wave, as we said before, like a complex wave is sort of like a dying exponential. And then the sort of the more like sort of the bigger this potential is, the more imaginary that number is, and so the faster you fall off.
Or the larger like your potential barrier is, the more it dies off as it progresses on. So again, the less chance that something will actually tunnel through. But yeah, so if you want to understand this completely, you might have to go through the mathematics. But sort of hand wavingly, you can see how it works if you understand quantum mechanics, or sorry, if you understand complex exponentials at that level. Yeah, you have a question?
Yeah, so like, so we say like a wave.
Mm-hmm.
Are we describing like the motion of the particles, or are we describing like sort of the energy?
We're not describing the motion of the particles. I think I can sort of say you're describing the probability of where the particle is, and I think that's like the best way to describe it in this case. And the probability of where the particle is, of course, is related to like quantities like energy and momentum, and that's where quantum mechanics really comes from, right?
So the wave, like in that sense, like what exactly is oscillating? Like what is like?
Nothing is really oscillating per se. We're describing where the particle is in a lot of these situations with waves. So we're saying that there's like, if you were to like, the math actually works out rigorously that if you square the wave that we're talking about here, you end up with the probability of where the particle is.
Like the way to sort of think about it is, remember electromagnetism, right? So we go back to the second lecture, and you have light, right? And light, sort of has a bunch of, so light is like an electromagnetic wave. You can think of it like this, kind of, right? And so, but the wavelength of this light can be different depending on its energy, right? Like if you have very long waves, you have radio. If you have very short waves, you have UV or X-ray, right? It turns out the same is true of particles, and so you might, and so it's sort of like analogous, right? Like what is really oscillating? Well, it's like not very clear what's oscillating, but like higher energy particles have like a smaller wavelength in the same way that light has a smaller wavelength with higher energy.
Yeah, but you can also basically see like in situations like this, the wave that we're talking about, if you square the wave here, you end up with the probability of where the particle will be. If I have like an arbitrary number of particles, so and if I square the wave here, like I have a decaying exponential, this is the probability of where the particle is going to be. Again here, if I square like the wave, like that's the probability of where the particle is going to be. And sorry, yeah.
So the wave sort of describes the position.
Yeah. Again, like with the uncertainty principle, like the idea of like position being like where the wave is sort of
probability of where.
Yeah, the probability is a better way to put like the probability, the expectation value of position is like if you average over the wave, where you expect the particle to be is given by this wave. Basically.
Right. So it's like one very interesting question you might ask is, because we're sort of like glossing over a few details because we don't really want to talk about them so much, but like one thing that you should know is like this is sort of like a probability. What you should actually do is sort of take the length of the complex number and square it, right? And so one thing we're not showing you here is that even though like the wave looks like it's going up and down, really it's like the probability is not oscillating, right? the complex number is always like sort of a similar length, right? Might not be so clear, but yeah,
We'll try to answer that after class though, like to give you a more complete description.
final paper.
Oh yeah, okay, yeah. I think we put this up on B courses, and I think I might have mentioned it, but like there's a final paper for this class. It's due on the Monday of dead week, so and it's worth like a large portion of your grade, so you should get started as soon as possible.
Or what was formerly dead week.
Yeah. Oh yeah, good point.
Is it like we submit it online?
Yeah,
Yeah.
we'll post the submission link at some point. But
Oh,
we're
yeah.
still very far away from dead week.
So I think
I'd like
there's
to
a list
believe-
of prompts as well. Yeah, we want you to select prompts that you think are interesting from the list of prompts that we have and write. These aren't like tremendously long, but they're about like 4 pages, so they're like a reasonable length. But we really want you to talk about like, this is like the only major assignment of this class. You don't have a final exam or anything, and we're not like testing your knowledge, but we want you to be able to talk about like one of these topics that we list on. Like, do you have the prompts in front of you, Nick?
You can put them up.
Okay, yeah, I can like.
Yes. Leon.
Yeah.
So if we see a prompt and start writing,
Yeah.
and we have some questions that we cannot answer ourselves,
Yes.
should we shoot you an email? Should
Yes.
we meet up with you somewhere?
You're
Yeah,
very
we have
welcome to
office
do any
hours.
of those things.
Yeah. All like office hours are in the syllabus. Pizza, and like you can ask us a question on B courses. We can any of those options.
Thank you.
Let's see. And I believe we're also allowing you to come up with your own prompts. If you have like a particularly interesting idea for something that you want to write, you can also propose a prompt and write it about that. Let's see.
If no one else has any questions, I guess you guys are free to go. Remember to turn in your homework. Please fill in the attendance form. And yeah, if you have any more questions, feel free to stay after. It's a very confusing topic, but
It can be confusing, but it does make sense. It's not.
it's definitely like well known.
Yeah, one thing I've heard is if you were all the size of atoms, this would just be like, oh, why are we even learning about this? It's only because you're not the size of atoms that this stuff seems weird.
Yeah. Yeah. So I guess